Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Assalamu alaikum class. I hope all of you will be fine and enjoy good health. Uh, Today we will study the modeling of heat conduction phenomena. This is lecture number 2, modeling of heat conduction phenomena. In this lecture, we will study how the heat conduction in a rod can be described in terms of partial differential equations. We will start with some basic definitions and laws. The first and important law for this problem is the Newton law of cooling. I hope you students will be familiar with this law, Newton law of cooling. This law states that the heat flow the heat flow from hot object to cold object. The heat flow from hot object to cold object. For example, if we set two objects, object A and object B, and connect them with each other, let the object A have 100 degree centigrade and the temperature of the object B is 50 degree centigrade. Now what we expect and what this law says. This law says that the temperature, the heat will start flowing from the object A to the object B. Now look at these temperatures. If the heat flows from the object A to the object B, then definitely the temperature of the object A drops down, means it starts decreasing. And if the temperature the and if the heat flows from the object A to object B, then the result of this phenomena on the temperature of B is that the temperature of the B is increasing. In short, the temperature of A depends on time. With respect to time, it is decreasing, and the temperature of B decreases with respect to time. We can, if we want to write this thing mathematically, we can write it as UA, means the temperature of A is a function of time UA of T, and UB, which is the temperature of B, this is UB of T. UA of T means a quantity which depends on time, which decreases with respect to time, and this function is of course an increasing function. Our next definition is the specific heat capacity. I hope you may have studied this term in the thermodynamics. We will just repeat this. So what is specific heat capacity? Specific heat capacity is the amount of heat, the amount of heat per unit mass, the amount of heat per unit mass required required to raise the temperature the temperature of a body or an object by 1 degree centigrade. The amount of heat per unit mass required to raise the temperature of a body by 1 degree centigrade. This is represented by C. By C. Let's discuss this thing with an example. Assume we have an object which have specific heat C is equal to 2 units. Okay, the specific heat of this object is 2 units. 2 units. Assume the mass of this object is 1 unit. If the initial temperature of this body is 5 degrees centigrade. Now, what does this thing mean, the specific heat? If we provide 2 joules, 2 joules, yeah, 2 units, 2 unit of heat to this object, then the temperature of this object increases from 5 degrees centigrade to 6 degrees centigrade. Okay. Now, if the specific heat of the object is 3 and we provide 3 joules of heat to this object of unit mass, then the temperature of this object will increase from 5 to 6. If it is initially at 50 degrees centigrade, then it will be increased to 51 degrees centigrade. Okay. So this is basically the interpretation of the specific heat capacity. If we provide 4 joules of heat to this object, then the temperature of this object will increase from 5 to 7. Okay. Similarly, you can analyze it further. If you add 1 joule of heat to this object, then the temperature increases from 5 degrees centigrade to 5.5 degrees centigrade. Note that here the mass of this object is 1 unit. Now assume if the mass of this object is 2 unit, then if we provide 2 joules of heat to this object, what will be the effect on this temperature? Assume the mass of the object is 2, the input heat is equal to 2, the initial temperature is equal to 5, then the final temperature is equal to 5.5. Okay, we will discuss this in more detailed and we will discuss it more exhaustively. The input heat, the temperature difference, the specific heat, and the mass. All these quantities are interconnected with each other. The mathematical expression which connects all these quantities is heat is equal to C multiplied by M multiplied by delta T. Now, delta T must be clear to all of you. Delta T is actually the difference between temperature. let input heat is equal to 2, the specific heat C is 2, the mass of the object is assumed 2, then what will be the change? So delta T must be equivalent to 2 divided by 4, which is equivalent to 1 over 2, means half degree centigrade change will be occur in the temperature of this body. As it is clear from this one, the initial temperature was 5, and as we add 2 joules of heat to 2 unit mass of the object, the final temperature is 5.5. So it is 5, then it is increased by 0.5, so it is 5.5. Our next definition is density. Density is basically mass per unit volume. It is represented by rho and is defined as rho is equal to mass over volume. We can also plug the definition of the density in the previous relation and this relation. Okay, using the value of mass from this equation, mass is equal to rho into volume, we have this equation will become heat is equal to C multiplied by rho multiplied by V multiplied by delta T. Now focus on this small problem. Volume of an object is 5 unit. The specific heat C is 2 unit. The density of the object rho is 3 unit. If heat of 10 unit is given to the object, how much change in the temperature will occur? So basically we have the value of V is equal to 5 unit, the specific heat C is equal to 2 unit, the density of the object is 3 units, and the input heat is also given, which is 10 unit. So if we want to know that what will be the change in the temperature, so we have to use all these information in this relation. The next definition is thermal conductivity. Thermal conductivity. Thermal conductivity is actually the ability of an object to conduct heat energy. Mathematically or scientifically, we can define it as the amount of heat per unit time per unit area that can be conducted through a rod of length 1 unit where the temperature difference is 1 unit, 1 degree. Let's explain this definition with an example. Suppose we have a rod of length whose length is 1 unit. Suppose this rod is placed between two areas, area A and area B. Now, let us assume that the thermal conductivity of this rod is 0.5. We will use the symbol K to represent the thermal conductivity. Suppose we have a rod of 1 unit and it is placed between two surfaces A and B. And assume that the thermal conductivity of this rod is 0.11 degree and the temperature of the B is 10 degree, such that the difference between these two temperatures is 1 unit. Further, assume that the area of A is 1 unit and similarly the area of the surface B is also 1 unit. Okay. In this setting, if the thermal conductivity of K is equal to 0.5, it means that after 1 unit time, means after 1 second, 0.5 joules of heat travel from the surface A to the surface B. Okay. If the thermal conductivity is 0.7, it means 0.7 joules of heat travel from this point to this point. Now you may know that the thermal conductivity um, of copper is very high as compared to the thermal conductivity of a plastic or a wood. So this parameters basically describes the conduction property of the rod. Our next definition is heat flux. Heat flux is basically the amount of heat that flows per unit time from a surface. This term is basically also defined by the Fourier law. According to Fourier, the heat flux is proportional to the change and temperature across the surface. Mathematically, if U is temperature, then heat flux, we will represent it by HF, is proportional to du over dx. So later on, experimentation shows that the proportionality constant is actually minus k. Now we are ready to make the mathematical model for a flow of heat in rod. So uh, this amount of heat, look at this expression. Suppose this is, assume this is a rod and this is a cross sectional area A of the rod. So the heat flux, this quantity is actually the amount of heat which flows across this area per unit area per unit time. Means if the area of this surface A is 1, then HF units of heat flows from A toward the right in 1 unit time. Now let's start the derivation of the heat equation. Suppose we have a one-dimensional rod whose length is L, and um, we have a rod of length L, and let's make some assumption. Assumption A1: the rod is homogeneous. The rod is homogeneous. What does this mean? The specific heat of this rod is constant. Means the specific heat of the rod at each point is same. Assume this is the rod of length L. We will place it on the x-axis and between 0 and L. C is equal to constant, means the specific heat at this point is same to the specific heat at this point. Means the specific heat at all points are constant. Through this rod, specific heat is constant. Rho is equal to constant. The density of the rod throughout this range is constant. Thermal conductivity is also constant. Means the thermal conductivity of this portion and this portion both are same. The second assumption is, look at these specification. Um, Physically, this is possible when this rod is made of a single material. I mean, if this is totally made of rod, of iron or of gold, of anything, but of single material, then uh, I mean that the specific heat and the density and thermal conductivity of iron will be constant throughout the length. The rod is insulated. The rod is literally insulated. Means the heat flow only in the x direction. The heat does not flow out of the boundary. The rod is literally insulated, means the curved surface of this rod is insulated. Heat does not flow out of the rod to the environment. The third assumption is the rod is 10, means the temperature at all the point of the cross section is same. The rod is thin. This will help us to understand that if this is a cross section area, then the temperature at this point and the temperature at this point is same, and this is only possible if the rod is very thin. Okay, so under these assumptions we will now model the flow of the heat in this rod. Now, before going to the analysis of the derivation, let's analyze some important observation of the temperature of this rod. Let the temperature of the rod is U. If we represent the temperature of this rod by U, then it may be possible that the value of U is different at different point. Means uh, it may be possible that the temperature at this point is 10 degrees centigrade and the temperature at this point is 5 degrees centigrade. So it is possibility for the temperature to be different at different points. So in this case we can write U is equal to U of x, means the temperature is a function of x. The temperature changes with respect to the selection of s. Now assume that the left end where the value of x is 0. Assume that this end is fixed at a temperature T1 and this end is fixed at a temperature T2. So at this end the value of x is 0. So we can mathematically write U at 0 is equal to T1. At this end the temperature is fixed at T2. So we can write U at L is equal to T2. So this is our first observation. Assume at time t is equal to 0 the experiment starts. Then and assume that um, with the passage of time the temperature of the rod changes. Means that if that at t is equal to 0 the temperature of this rod is 10, then it is possible that the heat will then of course the heat flows from this direction to this direction. So what will be the effect of this phenomena on the temperature at this point? With respect to time, it is possible that the temperature of the rod at this point may change, and this observation is at every point of x. So orally speaking, we can say that temperature of this rod at time t is equal to 0. If we start this experiment, then what do we expect? We expect that the heat will flow from this side to this side if the temperature of this end is high and this end is low. In that case, the temperature at any point x may change with respect to time. At time t is equal to 0, assume that it is 10. Then it may be possible that at time t is equal to 1, it increases or decreases. And at time t is equal to 2, it becomes 8. So we can model this phenomena by making a new variable u is equal to u at x and t, means the temperature of the rod at point x depends on the time variable t. So utilizing this terminology we can write these two conditions as u at 0 t is equal to t1, u at l t is equal to t2. Now, assume that at the start of the experiment, the temperature of the rod is represented by f of x. So, it is the start of the experiment, so we will set time t is equal to 0. We will write u at all points x and time t is equal to 0 is f of x. Assume this is the initially described temperature, initial temperature. This temperature must be compatible with these two conditions. Okay, if we substitute x is equal to 0, then f of 0 and t1 must be same. If we substitute x is equal to L, then f of L is equivalent to T2. Assume this is the rod, the temperature at this point is T1, temperature at this point is T2, and the initial temperature of the rod is this one. Means the temperature at this point is assume 90 degrees centigrade. The temperature at this point is assume 100 degrees centigrade. Similarly, this point is again 90. Now we start experiment by this setting. Then what will be the behavior of the temperature at this point? So basically Newton law of cooling is applicable here. The temperature of this side of this point is greater than the temperature of this point, so this point is called relatively to this point, so the heat will flow from this point to this point. The heat will flow in this direction. Okay, now what we expect at this point, the temperature at the left of the point x1 is very high as compared to the temperature of the x1, so this is cold object as compared to this one, so the heat will flow from this object to this object. Roughly speaking, the temperature of this point will increase and the temperature of this point will decrease according to the Newton law of cooling. Consider the same rod. Assume a small portion of this rod between 2 points. Suppose the first point is x and the another point is x plus del x. If this is x and this is x plus del x, then the length of this small portion is of course delta x. Now what is the amount of heat at this cross section? If the temperature of if the temperature at this point is given and we want to calculate the amount of heat at this cross sectional area, so we will just use the previous observation. The amount of heat is C rho A into temperature at the point x and t. This is the amount of heat at point x is equal to this one. Now if we want to calculate the total heat of this small portion, what will we do? We will integrate the quantity from x to x plus del x. this is the total amount of heat at general point x. So if we change the value of x, we will gain the heat at other points. If we substitute here x plus delta x, then this quantity is the total amount of heat at this point. So in order to calculate the total heat of this small portion, we will integrate this quantity from this x to x plus delta x. So this is the total heat in this small portion. Now what is the why will be the heat of this small portion changes? So let's first calculate the rate of change, or the rate of total heat energy in this small portion. So rate of change of total heat is equal to d over dt. So this is the uh, rate of change of total heat in this cross section. Now from elementary calculus, we can write it as integral from x to x plus del x c rho a ut of xt dx. This is the total rate of change of heat energy in this small portion. Now what is the heat flux at this point? Heat flux at x is equivalent to minus k multiplied by a into partial u over partial x at point xt. When we have unit area, the heat flux is minus k into du over dx. So um, if the cross sectional area is a, then the heat flux at this specific point is minus k a into partial u over partial x of xt. It means the total heat which passes from the point x in the right toward the right in 1 unit time is given by this relation. If you want to calculate how much heat is passing through point x in 1 unit time, so we will calculate this quantity. Okay. Similarly, we can also analyze the flux at this point, at the other point, the heat flux at x plus delta x. This is equivalent to minus k a partial u over partial x plus del x t. These are basically the flux at these 2 points. Now, if we apply the law of conservation of energy, the law of conservation of energy states that the change the the net change of heat in this portion is equivalent to the net change in flux across the boundaries. Law of conservation of energy states that net change of heat net flux is equivalent to the net flux of heat across the boundary. already calculated this quantity. The rate of change of heat, total heat, is given by this relation. This is equivalent to the net flux across the boundaries, means the flux at so the flux at this point minus the flux at this point. So the flux at this point is basically this one, and the flux at this point is basically this one. Now we can simplify this as Ka into partial u or partial x at x plus del x t minus partial u or partial x at x t, and the left hand side becomes x to x plus del x c rho a ut xt dx. Okay. Now let's recall a very important theorem from the calculus and the real analysis. The the mean value theorem. The mean value theorem states that if there is a function which belongs to this class, then there exists a value zeta in the domain AB such that this is the first main value theorem of the integral calculus. We can apply this theorem or this integral. So if we apply this theorem to this integral, how does it can be interpreted? There exists a zeta between these 2 points such that the integral is equivalent to 0 a ut f of zeta and to b minus a. So b minus a becomes delta x. We will write this part as it is. We can cancel this term, and after simplification and means divide by del x and apply del x approach to 0, what we get? We get ut at xt is equal to k over 0 to u double x at xt. Now if this quantity is divided by delta x and if we let delta x approach to 0, so this is basically the definition of second derivative. Let's use another notation. Ut is equal to alpha square u double x. Alpha square is basically equivalent to k over c rho, and this is called diffusivity constant. Now the temperature profile satisfy this equation. The temperature profile of this rod satisfy the second order partial differential equation. This equation is called heat equation. We can combine this equation with the boundary conditions, with these boundary conditions and this initial conditions to construct uh, a suitable set of equation. We can write ut is equal to alpha square u double x combined with u at 0 t is equal to t1, which is the temperature of the left side of the rod. U at lt is equal to t2, which is the temperature of the right end of this rod, and u at x0 is equal to f of x, which is the temperature of, which is the initial temperature of the rod. So this is the derivation of the heat conduction equation. I have tried my best to explain each and every term of this derivation, but as you know, we are not so expert in mathematics, so we will try our best. And if you have any suggestion, you can ask me, you can send me emails, or you can send me messages, so I will try to reach all of you. I wish a very good health for all of you. Stay blessed. Allah Hafiz.